Question number 3, what we have here is organic chemistry reaction. So as you know, this is ethanol, and this is delta minus and delta plus. And what you're doing is you are adding the HCN onto the aldehyde, such that what you get is you get a what did you call this again? I forgot what you call this already. Cyanohydrine. So it's got an OH, it's got a CN on the same carbon. This is a result of nucleophilic addition mechanism. The mechanism is nucleophilic addition, but the type of reaction is basically addition reactions, as stated in the introductory organic chemistry bit. What do they want us to do? They want us to use some bond energy from the data booklet. So if this is in the present 2022 syllabus, the data booklet data itself will be in the question paper. So you need to know that you get the data from inside the question paper. Perhaps at the end of the question paper or at the beginning of the question paper, you would definitely have the data somewhere. Now calculate the enthalpy change for these reactions, include a sign with your answer. So if we think about it, we are not told that everything is gaseous state, but if we use bond energy, that's because the question asks us to use bond energy. So I'm just going to display the bond so that we can see exactly what is happening from left to right. So display formula means show all the covalent bond. Why do we do that? Because we want to see exactly what happened going from left to right. So that is essentially what happened there. So going from left to right, you can hopefully see that, what do we have? We are breaking the CO double bond, and then we are forming a CO single bond. Perhaps I should use a different color. And we are breaking this HC bond. So I'm going to use a green, no, green is not good, a blue color to represent the bond we are forming. We are forming that. And what else are we forming? We are forming the C and C covalent bonds. So we break that and we form the OH covalent bond, and we break the CH and we form a CC covalent bond there. Of course, this reaction is catalyzed by a small amount of NaCN, could be KCN, because that thing is a nucleophilic, a much more nucleophilic source, which is a full ion compared to this being a simple molecule. So I'm going to have a look at my data booklet, because this is still question from the old syllabus. Of course, the new syllabus, you will have the data like I said in the question paper itself. So the red one is what we need to break. In terms of bond energy, we know that the enthalpy change of reactions is the sum of bond energy broken, whatever you need to break, minus the sum of the bond energy that you need to form. So in terms of what you need to break, let's see, what do we need to break? We need to break a C double bond O. Gotta choose the right one. C double bond O. 740. So I break one of that. I break one of that C double bond O. I also need to break one of the CH covalent bond. So that is 410. So I use a bracket to close up the bond energy that I need to break, and then I take away the bond energy that I need to form. These are CO single bond, so there's 360, and there's 360 multiplied by 1, and then I have one of that carbon-carbon single bond, that is 350. And what do I have altogether? Just need to move that up a little bit, and let's just press that and key that into calculator. So my first addition give me 1150, and the second one give me 710. So 1150 minus 710. Of course, your calculators show you 440, but you know, include a sign. Even when they don't say include a sign, you know the enthalpy change has a sign, a value, as well as a unit. So always be aware of what you are calculating there. Now the product of this reaction shows stereoisomerism. We know that stereoisomers refer to molecules having the same molecular formula. So they have the same molecular and also structural formula. That is why they are not called structural isomers. They are called stereoisomers. So they have the same molecular and structural formula. But what is different? They have different arrangement of atoms, all groups of atoms in space in 3 dimensions. So different arrangement of atoms or groups of atoms in 3 dimensions in space. Now, what about chiral center? So we know chiral center is a carbon atom which is bonded to 4 different groups or atoms. And they will give rise to enantiomers, which are the non-superimposable mirror images of each other. That is another definition you have to know. So these chiral carbons bonded to 4 different groups of atoms. 4 different atoms or groups of atoms. Okay, I think I've gotten them mixed up a little bit. So 4 different atoms, or it could be groups of atoms, and as a result you get enantiomers. Enantiomer is another word you need to know. Like I said, enantiomers are basically the pair of optical isomers that are mirror images of each other, non-superimposable. Now why is it that the 2 optical isomers are produced in equal amount? That is actually what you call racemic mixture. You will learn more about this in organic synthesis as part of chemistry. One of the popular questions they like to ask is something like that. Well, if you think about this reaction here, you do get a chiral center here on this carbon. Carbon form 4 bond, CH3, CNOH, and this is skeletal, so there's a hydrogen which is not shown there, which is there. And you started from this CO carbonyl, that is a carbon sp2 hybridized center. So it's a trigonal planar center there, and after that you get this thing which is tetrahedral. So if I think about the mechanism, so you have C double bond O there, so you have a hydrogen and then you have a CH3, so it's trigonal planar like that. And what happened then, that is the pi bond. The pi bond is a sideway overlap of orbitals like that. But what we can imagine is we need to break this pi bond obviously, but this thing is trigonal planar. So what it means is the nucleophile, the lone pair on the CN of the CN minus of the catalyst is the one that can kickstart the reaction. It can attack from the top or it can attack from the bottom. So what we can say is the starting aldehyde, the starting reactant aldehyde, RCHO. So the starting aldehyde has a trigonal planar carbon sp2 at the carbonyl carbon. So the C double bond O is the carbonyl carbon there. This allows the Cn minus nucleophile to attack with equal chances. So it's about the equal chances or equal opportunity that result in equal proportions of the resulting optical isomer, where you have one where the Cn minus will attack from the top and therefore it will be stuck on the carbon from the top, or the Cn minus attack from the bottom and the Cn, the carbon there, will be formed at the bottom face there. So they attack with equal chances. Onto the carbonyl, and therefore you get a racemic mixture. So even though you get an optical isomer, they are called optical isomer because they have optical activity. They will rotate plane polarized light, but because you get a racemic mixture where you have equal chances of the nucleophile attacking on these, and therefore you get equal amount of the enantiomers, the mirror images, so they will rotate plane polarized light in opposite directions, even though you have a chiral center, even though you will get optical isomers, but you have a racemic mixture where they rotate plane polarized light in opposite direction. Racemic is actually a word in optical isomerism topic in AS chemistry. Now, organic chemistry will almost not be complete without them asking you to draw mechanism, the usual nucleophilic addition mechanism, partial charges or full charges as well, because we're going to be talking about oxyanions. The lone pairs are important for the nucleophile. The curly arrows are important for your mechanism. So the first thing you start out from is this Cn minus. So it's got a negative charge there, but it's not the negative charge that actually attack. It's actually the lone pair on the carbon. So it's the lone pair on the carbon that will attack the carbonyl. So what we have there is a delta minus on the electronegative oxygen, leaving a delta plus on this carbon there. So what happened is the lone pair on the carbon with the Cn minus will attack the poor in electron, and then it will break the CO double bond. Having done that, what I have now is a carbon and then a Cn like that, because I don't break the C triple bond end. In fact, I form a C single bond C. I just break the C double bond O there, as you could see from the mechanism. So what I get then is O minus, because the 2 electrons go to the oxygen. Now the oxygen forms single covalent bond. It has a lone pair there. I must label my dipoles on the HCN polar molecule. It's not ionic, it's polar. Now what happened is the lone pair on the oxy anion attacks the poor in electrons, and now it breaks and gives the 2 electrons back to the carbon, and I will regenerate the Cn minus, and this thing has a lone pair of the carbon again, and they can attack more of your aldehyde starting material until all the aldehyde has been used up, and you will kick out another Cn minus, and having done that, you will regenerate back the catalyst. So explain why the Cn minus is a catalyst, because at the end of everything, you will always get back one Cn minus. It's not the original Cn minus from the NaCN or KCN catalyst, but regardless, you still get Cn minus. Chemically is unchanged, physically it might have changed, but chemically it's still the same. There's the property of it acting as a catalyst. Now this thing is called an oxyanion intermediate. So it's not your usual carbocation intermediate. This is one mechanism in which you have the negative charge on the oxygen there. Explain the role of the NaCN. So the NaCN is acting as a catalyst. So it acts as a catalyst, and it's just to speed up the reaction. So Cn minus is a much better nucleophile because it's fully charged compared to that polar molecule than HCN, which is a poor nucleophile. So it's only polar, it's got dipoles, but it's not fully charged. It's a much slower nucleophile, obviously not very good nucleophile, very slow reaction without the catalyst to kickstart the reaction there. Okay, so it acts as a catalyst, therefore NaCN will speed up the rate of reaction, will make the reaction faster, it will speed up the rate of reaction. I'm sure acting as a catalyst will be good enough. Anyway, so that's it really for this 12-mark organic question.